Okay, so the factor theorem, which is very, very, very closely related to the remainder theorem. So to the right is the graph y equals f of x. Use the graph to state the value of. So what's f of negative 3? 0. What's f of negative 2? Negative 12. What's f of negative 1? What's f of 0? 6. What's f of 1? What's f of 2? So use the remainder theorem and the information above to determine the remainder when f of x is divided by each of the following divisors. So if I divide by x plus 3, now if we don't want to do the division, what can we work out? F of negative 3. And what's the remainder? Okay, if I don't want to divide by x plus 2, then I can work out f of negative 2, which is negative 12, okay, and so on, right? So we can fill in the rest of these. Something like that, right? Yep. When a polynomial is divided by a binomial, when a polynomial is divided by a binomial and the remainder is 0, then the binomial is called a factor, right? Anything that divides evenly into something is a factor of that thing. Examine the table in part B. The binomials that are factors of f of x are, right, what do we got? X plus 3, x plus 1, x minus 1, and x minus 2. The binomials that are not factors are x plus 2 and x. You should have found that f of negative 3 is equal to 0, since the value of the polynomial function is 0 when x is negative 3. So we say negative 3 is a 0 of f of x. So what are the zeros of f of x? Negative 3, negative 1, positive 1, and positive 2. Okay. There's a connection between the zeros and the factors. Examine your answers for parts C1 and D. C1, so there's the factors. And D, there are the zeros. So if the factor is x plus 3, the 0 is negative 3, and then. Based on your results, complete the following statements. If A is a 0 of f of x, which means if f of A is equal to 0, then what can we say? What can we say about x minus A? It's a factor of the polynomial, which in this case is f of x, right? Wrong page. Nothing looks familiar. And if x minus A is a factor of f of x, then what can we say? Hint. Okay, then A is a 0 of f of x, right? Another way to say that f of. If you can make a statement like this, so it goes both ways, right? It says that if A is a 0, then x minus A is a factor, and if x minus A is a factor, then f of A is 0. That's the biconditional, right? And we can state that in one statement, which is called the factor theorem. And the way to do the biconditional is by saying if and only if, which means you just read it both ways, right? You put one statement first, followed by the other, then you reverse them. So the binomial x minus A is a factor of a polynomial function if and only if A is a 0 of the polynomial function. In other words, x minus A is a blank of a polynomial function f of x, if and only if, so what goes in blank? It's a factor. So when you're looking at a biconditional, that's if and only if. It says x minus a is a factor of if and only if a is a 0. Then you read it as if x minus a is a factor, then a is a 0. And then if a is a 0, then x minus a is a factor. That's how you can put it into the two separate statements which were down here. Right? If a is a 0, then x minus a is a factor. If x minus a is a factor, then a is a 0. Sam needs to show, Sam, you need to show that x minus 3 is a factor of p of x is equal to x cubed minus 2x squared, etc. One way to do this is divide p of x by x minus 3 and show that what? What condition is met if it's a factor? The remainder is 0. And show that. Okay, so if we do a division and end up with a 0, the remainder is 0. If we get 0 for a remainder, then we know that the thing we divided by must be a factor. Another way to show that x minus 3 of a factor, excuse me, is a factor is to substitute 3 into p of x and show that what? So we're going to show that p of 3 is equal to 0. Use one of the above methods to show that x minus 3 is a factor of p of x. Okay, so there's space on here. We'll actually do both methods, right? So what if we're going to divide? What do we got? X, so 1 minus 2 minus 23, 16. And we're dividing by x minus 3. Okay, go ahead, do the division. Okay, so bring down the 1, bring down the 1, don't write a 1. It's 3, 1, minus 3, 60, 0. Yeah. I'm almost certain that's right, because I did get a remainder of 0. If I'd gotten a remainder that wasn't 0, and I said, hey, show it's a factor, and no, I'm not getting that. And the other way is substitute 3 into the expression p of 3, right? So we get 27 minus 18 minus 69 plus 60, which is 87 minus 87, which is 0. Okay, so p, no big surprise there, right? It'd be surprising if it wasn't 0. So the factor theorem says we can divide by x minus 3, get a remainder of 0, or we can evaluate p of 3, get a remainder of 0. And basic factor theorem really says if the remainder is 0, then that's a factor. Now that you know that x minus 3 is a factor, completely factor it. Okay, so what did we start with? Luckily, I can read it off of here, right? So x cubed minus 2x squared minus 23x plus 60 is equal to. So I know x minus 3 is a factor. And I know that the remaining factor is, it's got to be a degree 1 less, right? So it's x squared plus x minus 20. And that's factorable. X, what? And then, it's got to be minus 4. Plus 5 minus 4. Okay. Now, anytime you factor, check this, right? X squared minus 4 plus 5 is plus 1 minus 20. Okay? Don't lose a pile of marks because you factor this incorrectly, right? So always check any factorization. You don't need to check the x minus 3. We did that, right? We've shown x minus 3 is a factor. We've shown, using the remainder theorem, that here's the other factor, right? I can find that other factor. If you're required to factor p of x, so Ballsmean question said factor this cubic, right? Was it better to determine if x minus 3 is a factor using the method in 2a or 2b? This is 2a. So is it better to divide it and show the remainder is 0, or is it better to substitute in and get a 0? Where did this come from? came from over here. So it's better to divide it, right? If we divide it, get a remainder of 0, we've got, in this case, the quadratic factor, right? We have the linear factor, we've got a quadratic factor which can then be factored. So we can get the factored form. So it's better to do what? Divide it. Better to divide. So if we need to factor, then using division is a better method. Show that 6 is a 0 and express the equation in factored form. Okay, so if they're asking me to show that 6 is a 0, we can start with the huge assumption that 6 really is a 0, right? Because if it isn't, we will show that it's not a 0. So what method are we going to do? Divide or substitute or evaluate? Well, if we divide, we get the other factor, and then we can get the fully factored form, right? And that's what we want to do. So then express the equation in factored form. So what am I dividing by? X minus 6, okay, 2, x cubed, negative 7, negative 27, negative 18. And I expect to see a 0 here, right? If I don't, then we've shown that it's not a factor, or we've made some mistake. Bring down the 2, multiply, subtract, multiply, subtract, multiply, subtract. See what happens with a little bit of practice. Also, if you don't get a 0 there, you probably messed up a subtraction, right? You went like negative 7 minus negative 12, you got negative 19 or something. So watch out, make sure that you can subtract negatives. Okay, so what do we know now? Well, we know that g of x is equal to x minus 6 times what? 2x squared? Okay, and odds are pretty good as factors. This squared plus 2 plus 3 is 5 plus 1 is 3. Yep. Make sure you check your factorization. Okay? Because if you mess this up, this is, generally isn't necessarily going to stop there, right? It could be, and then state all the zeros and draw me a graph. Sketch it out. What's the y-intercept? And if those are wrong, then everything else is wrong from that point on. Determine the values of k and p. If f of x is equal to kx cubed minus 13x squared plus px minus 9 has a factor of x minus 3. Okay, so what do we know? If f of x has a factor of x minus 3, what do we know? We know that f of what? 3 is equal to 0. So we can say 0 is equal to k times 3 cubed minus 13 times 3 squared plus 3p minus 9. And you can see we're getting an expression in k and p, right? Which is what? So we get, let's flip things around. So 27k. What's 9 times 13? 90, 27, 117. Minus 117 plus 3p minus 9 is equal to 0, or 27k plus 3p is equal to positive 126. Dividing through by 3 because, hey, why not? We can. Okay. What are we? We're going to solve a system of equations, right? So I can simplify that equation. It's fine. What else do we know? We know that f of x has a remainder of negative 125 when divided by x plus 2. So what does the remainder theorem say? F of negative 2 is equal to negative 125. Okay, so negative 125 is equal to k times negative 2 cubed minus 13 times negative 2 quantity squared minus 2p minus 9. All right, so let's rewrite that. What do we got here? Negative 8k. 52 minus 52 minus 2p minus 9 is equal to negative 125. So all I've done is just flip the left and the right side. And then we've got negative 61 here, so negative 8k minus 2p is equal to, what are we going to do? Add 61? What's that going to give us? 64. Negative 64. And let's go 4k plus 2p equals 64. Wrong? What's wrong?
You reduce the 8, but not the 2 or the 64.
Oh.
The 64.
Much easier if we... There we go. All right, so then what? Obviously, elimination. Subtract. 74. That's all wrong. What's messed up?
Yeah. Positive 32.
Positive 32. Positive 32. That's better. And then 4k plus, no. 4 times 2 plus p is equal to 32. P is 24. Okay, so let's just go. K is 2. All right, if you wanted to check this, you could just go back and substitute in using your value of k and p, throw it into your calculator, like here, and just go 2 times, 3 cubed minus 13 plus, etc. Just see if you get 0. Same thing over there, see if you get 125. Okay. The integral zero theorem. The zeros of the polynomial function p of x are negative 3, negative 1, and 2. Write an equation for p of x in factored form. Okay, so we would say p of x. So what are the factors? If the 0 is negative 3, the factor is x plus 3. If the 0 is negative 1, the factor is. And if the 0 is positive 2, the factor is x minus 2. Simplified form. Multiply it out. If we're going to do that, I'm going to multiply the last 2 binomials together first, and then multiply. It doesn't matter, right? Multiplication is commutative. So this is x squared minus x minus 2. And then I need to go through and multiply this out. X cubed minus x squared minus 2x plus 3x squared minus 3x minus 6. And collecting terms. So we get x cubed plus 2x squared minus 5x minus 6. That's the simplified form, right? And simplified form of what? Of p of x. Throw those in all over the place. So what's the constant term here? Negative 6. If you divide the constant term by each of the zeros, negative 3, negative 1, and 2, what's the remainder? So what's negative 6 divided by negative 3? 2. What's negative 6 divided by negative 1? 6. What's negative 6 divided by 2? Negative 3. So what's the remainder for each of those? Just 0, right? There's no remainder. It goes in. That is, each of the zeros of p of x is a blank of the constant term. It's a number that goes into, it's a factor. Or as we say, it's a gazinta. It goes into. There's a Ma and Pa Kettle comedy from way before my time even. It uses gazinta. So gazinta is a factor. Write another factor of the constant term of p of x. So what's another factor of negative 6? Negative 2. Is this factor of the constant term also a 0 of p of x? Justify your answer. So how would we do that? You have two choices. Is it a 0? You can either evaluate or you can divide, right? What are we looking for? A remainder. The remainder theorem says if this is a factor, then what? What do you want to do? Divide or evaluate? Divide? Okay, what are we dividing by? So we're doing x plus 2, and we want to see if that goes into. What do we say? X cubed plus 2x squared, so 1, 2, negative 5, negative 6. 1, 2, negative 5, negative 6. 1, 2, 0, negative 5. So, is it a factor? No. Doesn't go into it, right? How else? You could have evaluated p of negative 2, also gotten a 4. Right? The remainder theorem would have said that that's the remainder, right, when you evaluate the polynomial. So, the integral zero theorem. If an integer a is a 0 of a polynomial function, then a is a blank of the blank term. So, if a is a 0, so here are these guys, these are the a's, they are zeros, then we say that they were what? They were a factor of the constant term, right? So is a factor of the constant term. Note, the converse statement is not true. Just because a is a factor of the constant term, it doesn't mean that it's a 0. Okay? So it works one way. If it's a 0, then it must be a factor of the constant term. Okay. One-way street, not an if and only if, right? Just because it's just because it goes into the constant term doesn't mean it is a 0. Okay. So for the polynomial function, so we call them potential integral zeros, right? They have the potential to be a 0. So what has the potential to be a 0? Any number which is a factor of the constant term, which is 15. What are the factors of 15? So plus or minus 1. What else? What else? What else? So it says if there is an integral 0, then it's one of these numbers. Okay, does that make sense? So if there is, there's no guarantee there's an integral 0, right? It doesn't have to be an integer. It could be a fraction, it could be, rational number. Another word for a fraction. But it says, if there is a 0 which is an integer, then it's one of these guys, right? It's not 2, it's not 4, it's got to be one of these. Express the equation of the function in completely factored form. So we need to find one of these guys which is a 0. Okay, and then what? Then we're going to divide by the corresponding factor. We're going to, at that point, verify that the remainder is 0, have the quadratic equation, and then we can do the factored form. Okay? Now, to figure out which of these we might want to try, we go with the other way, right? Say, well, let's try P of 1. Let's see if P of 1 could give me a 0, right? So P of 1 is going to be like 20 minus 32. Not going to give me a 0, right? Okay, what about P of negative 1? Well, it'll be negative 2 plus 3 will be 1. That'll be plus 30. Now, that won't work because the 32 and 15 is already 47. I can't get there. All right, so let's try 3. Now, at this point, you might go, putting 3 in there, why don't we just divide by x minus 3 and see what happens, right? It's fairly easy to fix. So having a pencil handy, right? So let's divide by x minus 3, which means we're trying positive 3 to see if it's a factor. We got a 2, we got a 3, we got a minus 32, we got a 15. We're looking for a 0 down here. Okay, so that's a 2. This will be negative 6, which will be 9. This will be negative 27, which is negative 5, 15, 0, huzzah. Okay, it worked, right? If x minus 3 didn't work, I can change this to a plus 3, just go erase this little bit of it, right? I mean, the rest of it's still good. Actually, these numbers are still good. They're just going to have opposite signs, but whatever. Right? It's easy to erase, and that might be easier than, okay, what's 2 times 3 cubed is 27. That gives me 54 plus 3 squared plus 27. 54 plus 27 is some biggish number, 50, 64, 74. It's like 81 minus 96, or 81 plus 15 is 96 minus 96. Yeah, okay, that'll work. You could also just try it on your calculator too, right? Go 2 times 3 cubed plus 3 times, etc. Okay, once you find a 0, however you find that integral 0, right? So we've listed them. We might ask you, list the potential integral zeros. And you'll say, I know how that works. They are factors of the constant term. So all I have to do is factor the constant term, right? What are all the factors of 15? 1, 3, 5, 15. Oh, wait, but it's plus or minus 1, etc. Okay, I found a 0, so now I use the remainder theorem. I show that this is a 0, which now gives me, I want factored form. What was the function? P of x. Okay, so P of x is equal to x minus 3. We know that's one factor. We got 2x squared plus 9x minus 5. And a 2x and an x, and plus 10. Right? 2x squared plus 10x minus 1 plus 9x. Yes. I'll get better at this factor every day. Okay, so always, always, always do what once you factor? Check the factorization. You're going to get the 5 and the 1. It's the only way you can factor 5 is a 5 and a 1. You could get these signs wrong. You could put the 5 and the 1 in the wrong place. So just check it out, right? 2x squared plus 10 minus 1 plus 9 minus 5. I'm good. Okay. Any factoring errors are generally going to occur because the signs are incorrect. You got the signs flipped around or whatever. Sketch the graph, labeling all intercepts. What's the y-intercept? 15, right? What are the x-intercepts? 3 and so negative 5, 1/2, 3. This is a cubic. It has a positive leading, so what's it doing here? Is it, well, it's down in 3, up in 1, right? So we're starting from down here. And we're doing something like that, right? These are all of multiplicity 1, right? There's no repeated factor, right? It's not like x plus 3 squared. Okay, that would be a multiplicity 2. You know, that we could do, if we took this thing and shifted it up a smidge, then this would end up on here, right? And we'd have some 0 there of multiplicity 2. How do we know they're all multiplicity 1 and they're not like 3 or? Straight through, right? Straight through is multiplicity 1. Bounce off, minimum multiplicity of 2. Could also be 4, 4, yeah. Okay, 1 is 1, right? We can always tell 1, it just cuts straight through. If it does this little curvy thing, then it is a minimum multiplicity of 3. Okay, when we do this stuff, we're always saying, what's the minimum multiplicity? Sure, it could be 5. Could also be 13, but we don't want to go there. Right? Say minimum, this is a 3, this is a 2, these are 1s, etc. For the polynomial function, express the equation in completely factored form. So what do you want to do first? What can we take out? We'll take out an x, right? So if we're going to factor, let's start by factoring. Okay, we factor out an x. Now if we look at the, what's left? Well, we got to factor this 3x cubed thing, right? How do we factor a cubic? We don't, right? We find a 0, we do the division, that gives us a factor. We find a 0, that gives us a factor, we do the division, that gives us a factor which is of degree 1 less, and then hopefully that actually factors. Okay, what are the potential integral zeros? The p's. What are the p's? Plus or minus? 1, 2. Keep going. Okay, they're going to kind of pair up, right? Like 1 with 16, and then 2 with 8, and then 4 with 4. So we're not going to do the 4 twice, right? We'll just. Okay, so we might, it's always a good idea. Let's start with 1. What are we going to get? 3 minus 8 minus 4. We're going to get like 19 minus something. So 1 isn't going to work. Negative 1, that'll flip some signs, right? This will become negative 3. Minus 8 is negative 11. Plus 4, plus, no, that's not going to go right, because that's going to be like plus 20. So not that. 2, I don't know. Let's just try dividing by x plus 2 and see what happens. Okay, 3x cubed minus 8x squared minus 4x plus 16. 6. I almost hope this doesn't work. We can go to negative 2. Okay, what's that? Negative 14. I don't think this is necessarily going to work. Negative 28, 24. Not going to work, right? Okay, so let's try what? Let's try x minus 2. Negative 6, negative 2, 4, negative 8, 16, ha. You want to know how to cheat? Just graph it, find a 0, throw it in there. Okay. Say that out loud. Yeah, you can just go in and graph 3x cubed minus 8x squared minus 4x plus 16. You're looking at one of anything that's a 1, a 2, a 4, an 8, or a 16. Find one of those, then do this, right? How'd you figure out that 2 is a 0? Well, I just tried stuff and look at work. Okay, so it's my factored form. What was my, what is this thing, p of x? So p of x is equal to, we have a factor of x, we have a factor of x minus 2, we have a factor of 3x squared minus 2x minus 8. Ah, 4 and 2 maybe? Sure, because I can get a 6, 4, minus, plus, done. But I better check that because I just kind of think that's what it is. Minus 6 plus. Yeah, it is. Okay, don't care how you factor. So if you want to do over the rainbow, whatever method, the little box method, find your own method. Just doesn't matter, right? That you are able to factor correctly and completely is all that matters. Okay? How you choose to do it, the method you use. Mine is called guess and check. Sketch the graph of the function, labeling all intercepts. What's the x-intercept? Oh, sorry, what's the, wait a second, that's the wrong question. What's the y-intercept? No, 0. Of the original function? No. This is the function. Right? Here's your y-intercept. Okay, that's my y-intercept. It's also an x-intercept. See, it's this guy here. Okay, what are the other, what do we got? 2. Oh, and 2 again. Wait, maybe we should rewrite this. X minus 2 squared, 3x plus 4. So we have a 0 at positive 2, but it's of multiplicity 2, right? And where's our last 0? Negative 4/3. Okay, so we got a 0. This is of degree 4, and the end behavior is, where does it start? Where does it end? Or so it's up in 2, up in 1, right? So it's coming from here. So it's going to come down through here. So it's coming here, comes down, comes back up, does a little touch and go. There's your degree 2, multiplicity 2, multiplicity 1, multiplicity 1. Okay? If you graph it, it's going to look something like this. Okay? I don't know where this is, or this. I do know where this is. I don't know where these 2 guys are. There are ways to do this, right? Many of which shall be revealed in the next math course. Right? How do you know? Well, I can tell you. Read page 131, example 4.
I never saw that.